Oh, thank you. Okay, hello students. This PowerPoint is about matrix, inverse matrix, and the identity matrix. Okay, I'm going to cover the basic matrix operations. I believe it's from section 6.4, and matrix product and inverses are from section 6.5 on the 1324 book. I'm going to cover real life example. Determine dimension size of a matrix, matrix addition, matrix subtraction, scalar multiplication, and how we can use it like in real life applications. And then for the matrix product and inverses, I'm going to cover matrix multiplication, the identity matrix, and inverse matrices. All this information is kind of a lot, but I try to get the most important things in the hour that I have, or the 50 minutes that I have. Okay, matrices are important in the field of management, natural sciences, engineering, and social sciences as a way to organize data. So matrices are used on a daily basis by companies to organize some data. Okay, now this is an example. I'm going to start you off how we can use a matrix with example number 1. Furniture manufacturing. Let's say the Easy Life company manufactures sofas and armchairs in 3 models, model A, B, and C. The company has regional warehouses in New York, Chicago, and San Francisco. In its August shipment, the company sends 10 Model A sofas, 12 Model B sofas, and 5 Model C sofas, 15 Model A shares, 20 Model B shares, and 8 Model C shares to each warehouse. Okay, how can we organize the data? These data might be organized by listing them as follows. Okay, you see we have sofas. The sofas were, let me see here, sofas, we had 10 Model A, 12 Model B, and 5 Model Cs for the sofas. And then for the chairs, we have 50 Model A, which is right there, and then 20 Model B, we got it from that information, and 8 Model C. So we can organize this data just the way I did it right there. And then it can be done like in a tabular, like in tabs. You see, for example, this is a furniture, sofa, and chair, and this is a model A, B, and C. So, for example, here we have sofa model A, sofa model B is 12, and sofa model C, we have 5. Same thing with the chairs. So this, we can put it into a matrix. Okay? So the matrix is, let's call it matrix M, will be 10, 12, 5, and 15, 28. So this is how we can organize this data into matrices. Okay, now, the rows refer to the furniture, as we can see back here on the tabular, and the columns refer to the model chairs, which is A, B, and C. Okay, matrices. Because matrices can have a whole bunch of rows and a whole bunch of columns. So this is really the notation, like for say matrix A, this is the first column, first row, first column, first row, second column, and so forth until you have the end column on each row. And same thing with matrix B. Okay. So matrices are denoted by capital letters. Okay, or uppercase letters. For example, A, capital A denotes a matrix, and also capital B. And the small letters, it means they're like the elements that are inside the matrix. Okay, lowercase letters are used to name the elements of the matrix. Example A, I mean little a for matrix A. So all the little a's or lowercase a's belong to matrix A. And now the lowercase b's belong to matrix B. So these are all called elements. Okay, now, a matrix. So matrix, they're like done in rows times columns. So for example, that's the order that you're going to put in rows, right? So we count the rows, and then we count the columns. And the elements, for example, the position of the element, this means element A is in row 1, column 1. Okay, the letter stands for position is row 1, column 1. Position A14 means The 14 stands for position row 1 again, and column 4. So what do you think A23 is? A23. Anybody? A23?
It's gonna be 23, then row 1, column 23.
Yeah, pues it'll be right here. 23 will be this right here. 23 will be right there. Okay, so it should be row 2, column 3. Okay, right now I'm going to give some examples with with the real matrices. They so you know about the positions of the elements. And here we go. Okay, what is the position of the following elements? For example, A13. What would it be, guys? Somebody? What number? What will be the position?
13.
Now, A13 means, this means row 1, column 3. So, Christina, where is row 1? Right, this is row 1, and this is row 2. So row 1, column 3, wouldn't it be, this is row 1, this is column 1, column 2, column 3. So the answer will be 3.
Okay.
Okay? Now, A24. A means row 2, which this is row 2 here, and column number 4. 1, 2, 3, 4. So my answer is 8. Okay? Now, the dimension of a matrix, or the size of a matrix, is rows by columns. The number of rows times number of columns. Okay, that means by, okay, like times rows times columns. For example, determine the order of the matrix. So this order, you have 2 rows and 4 columns. So that's why it's a 2 by 4. Example 2, determine the dimension of the matrices. Okay, anybody, how about the matrix on the left? This one here, what will be the size of it, or the dimensions?
3.
Yes, Christina?
Is it 3?
3 by what?
By 3.
Very good. 3 rows and 3 columns, 3 by 3. Okay, how about the one in the middle? What would it be?
1 by 3.
How many rows do we have?
1, 3.
3, right? So 1, 2, 3. So we'll be a 3 by 1.
1 by
How about the last one?
1 by 1.
How many rows do we have?
1.
How many columns?
1.
Oh, come on, 1 column. We have 1,
2, 3.
2, 3. 1 by 3, right?
Yes.
Does that make sense?
Yes. I'm still
Okay.
confused with the rows and the columns. That's why.
Okay. How about this one then? How about this one?
Oh, it's
How many rows?
4 rows and 2 columns.
Very good. There it is. So you guys pass the test, okay? I'm going to move on.
Okay.
If you want afterwards, if we're done early, the tutors or I can show you some more examples until you feel satisfied that you understand what you're doing, okay?
Okay.
Okay, now matrix operations. Again, this is a notation for the matrix, right? Because it can be like a very long matrix, like infinite rows and infinite columns, right? But there's always has to be finite. But this means that whatever matrix it is, that's what this notation denotes. Okay. In order to add or subtract matrices, the matrices must be the same size. Okay. So again, in order to add or subtract, they must be the same size. Okay, let's do this. So let's do A plus B. Okay, from here. We have, so to add them, you can add the first, the element on the first row, first column on matrix A, plus the one on B, first row, first column. That's why it's A11, A11 plus B11. And this is going to be, again, A12 plus B12, which stands for the first row, second column on matrix A, plus same row 1, second column for row B, and so forth. Okay, that's how we add them. Okay. And right now we're going to do some real examples that I got, I think, from the homework. See? So you keep going until you finish. But remember, this is very important here. The matrices must be the same size in order for you to add them or subtract them. Okay? Matrix addition. The sum of two m by n matrix, m stands for rows and n stands for columns. Again, the sum of two m by n matrices, x and y, is the m and n matrix, x plus y, in which each element is the sum of the corresponding elements of x and y. All that means is this right here. You see, for example, a matrix A and matrix B, right? If they're the same size, you can do the operation. So all we do, we're going to add the first row, first column on matrix A plus first row, first column on matrix B. That way the same here. And same thing with subtraction. Subtraction means that you're going to be subtracting them. That's how you're going to be doing the same thing as addition, but subtraction. And matrix subtraction is the difference of two m and n matrices, x and y, is a m times n matrix, x minus y, in which each element is the difference of the corresponding elements of x and y. These are like the definition that I got from the book. At times, these can be confusing because at times the student doesn't understand the notation. For example, remember guys that capital letters denotes matrices. That's what the x plus y mean in capital letters. And the corresponding elements, it all means that like for example, again, that A11, you have to write it with B11. And A12, you have to write it plus B12, which stands for the first row, second column, and so forth. That's what that means right there. Okay. Okay, now, some examples here. Remember, guys, if they're not the same size, you cannot add them or subtract them. So first, the most important thing is to get the sizes right away, right? So this is a 2 by 3. That's also a 2 by 3. How about C? Anybody? Can somebody tell me the size of it?
2 by 2.
Very good, very good. How about D?
2 by 2.
2 by 2. Excellent. Okay, now, what's A plus B? Can we add them? These two. Are they the same size?
Yes.
So we can do the operation then. So then, okay, we're going to do 1 plus 8 goes in row 1, column 1. And then negative 3 plus 0 goes in row 1, column 2. And then 2 plus 1 goes in row 1, column 3, and so forth. Same thing, 2 plus negative 1, and 2 plus 3, and negative 1 plus 4. Okay, now, this step, you can actually skip it if you want. But I'm just showing you so you guys can see what actually takes place. But I can go like this. A plus B will be the same thing as 1 plus 8 is 9. Negative 3 plus 0 is negative 3. 2 plus 1 is 3. And 2 plus negative 1 is 1. 2 plus 3 is 5. And negative 1 plus 4 is 3. So that's the sum of matrix A plus B. Okay. Now how about C plus D? Can we do the operation? Are they the same? Yes, they are correct. So we can add these. So again, we're going to add 5 plus 2, 1 plus negative 1, negative 4 plus 9, and 3 plus negative 7. And again, you can go straight. I'm skipping the step. You can just go 5 plus 2 is 7. 1 plus negative 1 is 0. Negative 4 plus 9 will give us 5. And 3 plus negative 7 will give us negative 4. And again, you can do this step. If you're confused, but this is showing all the work. But you can go from here, C plus D, to the answer. Okay. How about A plus C? Can we add A plus C? A is 2 by 3, and C is 2 by 2. Can we add them? Somebody.
No.
Very good, very good. No, we can't. So not possible. Make sure that you know, the way you can do the operation is only if they're the same size. And I emphasize, that's really important for students to know. Not the same size, okay? Okay, now, subtraction. Subtraction is the same thing, right? They have to be the same size. So again, I do the same matrices, but this time we're going to subtract them. A minus B is going to be 1 minus 8 on the first row, first column. And then negative 3 minus 0 on the first row, second column. And 2 minus 1 on the first row, third column. And same thing for the second column. For the second row, it's going to be row 2. Second row, and first and the first column, right? So it'll be 2 plus negative 1. And it's going to be 2 minus 3. I'm sorry, it's subtracting. And then negative 1 minus 4. And again, same, this will be row 2, column 3, plus row 2, column 3. So my answer will be 1 minus 8 is negative 7. Negative 3 minus 0 will be negative 3. 2 minus 1 is 1. And 2 minus negative 1 is 3, because when you have a negative, right, minus a negative, this turns to positive. This will be negative 1, and this will be negative 5. How about C minus D? We do the same thing as before, but instead of adding, it's going to be subtracting. 5 minus 2, 1 minus negative 1, negative 4 minus 9, and 3 minus negative 7. Okay, so this will be 3. And again, this turns to addition, so 1 plus 1 is 2. These two, they're both negative, so we add them and keep the sign, so it'll be negative 13. And again, this turns to a positive, so that'll be 3 plus 7 is 10. Well, that's my answer. Can we do A minus C? Are they the same? No, right? So not possible. Not the same size. This is real straightforward. Okay, where students have a little bit of issues is when you multiply, but I'll get to that later. Okay, now, here comes the scalar multiplication. The scalar multiplication is a product of a scalar k and a matrix x is a matrix kx, in which each element is k times the corresponding element of x. Okay, so for example, find 6x. This is my x here, right? This is my x, the matrix x. So 6 times the matrix x, you're going to multiply 6 times every element in the matrix. So 6 times 2, 6 times 0, 6 times 5, 6 times 4, 6 times negative 2, and 6 times negative 3. So 6 times 2 will give us 12, right? And then 0, 6 times 5 is 30, 24. 6 times negative 2 is negative 12, and 6 times negative 3 is negative 18. That's my answer. Okay, now, find negative x. Hey guys, or negative matrix x. Isn't the negative x the same thing as like a negative 1 that's just like invisible negative 1, but we don't see it? Okay. So here, you can do it. Here, when you have a negative, all you do is switch the signs inside the matrix of each element. Because negative 1 times 2 is negative 2. Negative 1 times 0 will give us 0. Negative 1 times 5 will give us negative 5. Negative 1 times 4, negative 4. Negative 1 times negative 2 is 2. Negative 1 times negative 3 is 3. Again, observation. The observation, when you have just like a plain negative in the front of the matrix, the observation is the signs of every element inside the matrix switching. You see it went from positive to negative. The 0 stays at 0. Positive 5 goes to negative 5. Positive 4 goes to negative 4. Negative 2 goes to 2. And negative 3 goes to positive 3. Only when you have like a negative or a negative 1. If you have like a negative 2, then you have to multiply the negative 2 times every element inside the matrix. Okay? Okay, now. So it says here, example 6, it says let A, matrix A, be negative 2, 0, 5, 3, which is a 2 by 2 matrix. And let matrix B be a 2 by 2 matrix, which is 0, 2, the first row, and 4, negative 6, the second row. Find each of the following. Hey guys, this problem here, the number 3 is really both of, all 3 put together. But what I did, I first did this part here, the negative 4a, and then the 5b, then I'm going to add them. Okay, so let's do them one at a time. So for number 1, negative 4a is going to be negative 4, right, times matrix A. So again, here I'm showing you all the work, but like I said, you can actually go from here to the answer. Okay, because what's negative 4 times negative 2? Wouldn't that be 8? What's negative 4 times 0? Will be 0. Negative 4 times 5 is negative 20. Negative 4 times 3 is negative 12. But anyway, you can do it this way if you want. Okay, but most students, they actually just go from here to the answer. So this is negative 4a. Okay. Now let's try 5b. It's going to be in the same manner, right? So it'll be 5 times the matrix B. And again, 5 times 0, 5 times 2, 5 times 4, and 5 times negative 6. So it'll be 0, right? Because 5 times 0 is 0, 5 times 2 is 10, 5 times 4 is 20, 5 times negative 6 is negative 30. So that's the solution for 5b. Now let's put them together, right? So negative 4a, wasn't this my answer here? 8, 0, negative 20, negative 12, plus 5b was 0, 10, 20, negative 30. Now we apply the property that we learned earlier with adding matrices. So it's going to be 8 plus 0, and 0 plus 10. Negative 20 plus 20, and negative 12 plus negative 30. So that will give me 8. That will give me 10. That will give me 0. And that will give me negative 42. So that's my solution for negative 4a plus 5b. Okay. Now, let's do some like this applications problem from the first example that we started, but now they added a little bit extra information. Okay. Recall from the furniture manufacturing problem that the Easy Life company manufactures sofas and armchairs in 3 models. Remember, this was a matrix. Okay. But now this is what happened now. Okay. They got the shipment in August. Now during August, the Chicago warehouse of the Easy company shipped out the following number of each model, which the entries and the matrix have the same meaning as given earlier. Okay, so how do we find what's left? What was the Chicago's warehouse inventory at the end of September? I mean, this should have been August. Okay, that should have been August, I guess. My bad. Taking into account only the number of items received and sent out for that month. Okay, again, my mistake. This should be August. So if this was, when August started, right, and these went out or they got sold. So wouldn't it be matrix C minus K? So matrix C minus K will be matrix C minus matrix K. And again, we do the operations that we did earlier. Some examples how to do them. So it's going to be 10. 10 minus 5 is, right, is 5. Okay, now I'm doing it this way. 12 minus 10 is 2. 5 minus 3 is 2. 15 minus 13 is 2. 20 minus 12 is 8. And 8 minus 8 is 0. Okay, let me go back here. It just means, guys, that I think this with the sofas and this with the chairs, right? It was model A, model B, and model C. So after the inventory ended in August, right? This is supposed to be August. There were 5, right? These were the sofas. There were 5 Model A sofas left. There were 2 Model B sofas left, and there were 2 Model C sofas left. And these were the chairs. There were 2 Model A chairs left, 8 Model B 8 Model B chairs left, and also there were no Model Cs left, Model C chairs. Okay, that's how you will relate it in real life. Okay, now, very important information here. Multiplication of matrices can only be done under the following conditions. I was going to copy the definition of the multiplication, but to me that was too confusing for the students. So in other words, I'm gonna put it like in my own words. Okay. Say you have matrix A size and matrix B size. Say this is matrix A and matrix B. In order for you to actually do the operation, these the inner numbers, or the inner what's it called? What's the word in here? Because these are the rows, right? This is these are the columns on matrix A, and these are the rows on matrix B. They have to match. Okay, so what you do, you put the size on matrix A and you put the size on matrix B, and the 2 in the middle, they have to be the same in order for them to in order for you to do the operation. Must match. The solution will be the outer ones, which would be the M times P. So if we were going to do this matrix and multiply it, right, we could do it because these are the same, and the answer will be an M by P matrix. If the size of the matrix is 2 by 3, right? So say, for example, here, say matrix A is 2 by 3. Then matrix B must be what?
2 times
Right?
3.
3 by something, right? We don't care about the key here. It's gonna be a 3 by something. This can be any number. 3 by 1, 3 by 2, 3 by 3, 3 by 4. It doesn't matter. What matters is that the inner, right, determines if you can do the operation or not to multiply them. So the matrix will be 2 by whatever the number is right there. That'll be my solution matrix. Okay. Okay. Now, give the following matrices. State whether the matrices can be multiplied. Here, I'm not going to do is just put yes or no. Okay. So, for example, matrix A is equal to right. So, what size will that one be? Okay. Let me go back. Let me do them all here. Okay, this will be a 2 by 3, right? This will be a 2 by 2. How about C? What would it be? What size? Anybody?
3.
3, yes? 3
3
by
by
what?
2.
Very good, Christina. Christina, I think you got this ready, right? I think you got this. 3 by 2,
Yes.
very good.
Kind of.
Okay, now. Can we multiply A times B? Matrix A times matrix B. Check this out. Matrix A, it's always good to put them like this. Matrix A is 2 by 3, right? Matrix B is 2 by 2. Can we do the operation on this one? Can we multiply them?
Yes.
Are they the same?
Oh, no.
No, right? No, we can't. No match. So, cannot multiply. Okay? Hey guys, when you multiply a matrix, that's your first step. Put the size, but you have to put it on the same order. If it's AB, you put AB, because if you put BA, it might be wrong, because it might not be done. Okay? Okay, now B times A, right? So matrix B is 2 by 2, and matrix A is 2 by 3, right? Isn't this right? Like this is A times B, this is B times A, right? When you multiply real numbers, wouldn't it be the same answer? You see, but now with matrices. With matrices, they go by the order. You see, A times B is not B times A. You see, this one can be done. Yes, it's a match. And what's my solution matrix? Will be a 2 by 3. A times C, right? We have matrix A is 2 by 3 and C is 3 by 2. Can this one be done? What do you guys think?
Yes.
Very good, very good. So yes, it can be done. Okay, good job, Catalina and Christina, both of you guys. So it's a match. So this is my solution. Okay, it's going to be a 2 by 2 because the answer will be the outer, the outer numbers, right? So it'll be a 2 by 2. Okay, now, hey guys, right now hopefully we can finish the PowerPoint, and because I have a unique way of doing multiplication on matrices. And but right now I could not do it because the animation won't let me, because you're going to be it's very simple to follow. So hopefully we'll have time, and that way I can show you my method, okay? And my method that I modified is very simple, and all my students love it. Why? Because they say that it's easier than the book, okay? But I'm going to show you the way the book does it, because here, guys, I can actually do animation, but the way I do it, I cannot do animation. I have to show you, show you live. So hopefully we have a chance for that, okay? So we're gonna multiply matrix. These are the same ones from before, right? From the previous slide. So BA can be done, right? So it can be done, and what's my answer? When it be a 2 by 3. So this is how you do it, okay? This is how you multiply. Step 1. Right, I put the answer here because it's gonna be 2 rows and 3 columns. So step 1, okay? I'm going to get matrix B, right? So there it is. And then I'm going to put matrix A. So the way they explained it, guys, you see that's why I put the blue, and you're going to multiply times the red. So you're going to multiply the first entry here times the first entry, the first entry on the rows times the first entry on the columns. You're going to multiply 1 times 2. And then you're going to add it to the second entry on the rows times the second entry on the columns here. That gives me what? That gives me 2 plus 0, so the answer is 2, so the 2 goes there. Okay? Step number 2. If you notice, check this out, guys. You notice on the first step, we use column 1. On step 2, we use column 2. On step 3, we're going to use column 3. And remember, guys, earlier that I told you that it has to be like a 3 by something. Remember on the one that I said matrix B must be something by a number, right? Because this can go on forever, right? Because I can keep multiplying by column 4, column 5, column 6, column 7, because they're both only two. There's 2 numbers here only, because there's 2 columns and 2 rows. Okay. So here we're going to multiply the first entry here times the first entry on the columns, and then we're going to add it times the second entry on the rows times the second entry on the columns here. So it'll be 0 plus 0 will give me 0, and the 0 goes there. Okay. Step 3, you keep going right now. This will be step 3. Everything the same, but this is going to be red there because you're going to be multiplying by the 5 and the negative 3. Okay, and you keep repeating the process. So that'll be 5 plus 0. So the 5 goes here. You see, so we're done. I'm done with the first row. Why? Because there's no more columns to multiply by. So what do we do next? We switch them. We're done with our first row, right? Because you have to multiply the first row times every column on the second matrix. So then there's no more columns to multiply by. So then I go down to the second row. You see, so now the second row is highlighted in blue. So I'm gonna repeat the same process as I did in step 1, but instead of using row 1, I'm gonna use row 2. So 4 times 2 is right. So 4 times 2 plus negative 2 times 4 is gonna give me 0. So the 0 goes right there. Step 5. Again, we're using row 2, and now we're going to be using column 2. So 4 times 0 and negative 2 times negative 2. The answer will be 4. The 4 goes there. And then finally, step 6, we're going to do again second row times the last column. And this will be the last step because there's no more columns to multiply by. So 4 times 5 and negative 2 times negative 3. So that'll give me 26. That's how you multiply, guys. Hey, guys, I didn't do no more examples because this eventually has 70 animations, guys. So this slide alone took me about an hour because I wanted to make everything perfect. That way you guys can go back and actually to multiply, just follow the same procedure. Right now, I'm going to do another multiplication, but it's with the inverses. But hopefully, I'll have a time to do this very same problem on the board. And I truly believe you're going to like the way I do it, guys. Okay, the way I want to fight the multiplication because it's less work and it's more convenient for the students. Okay, that's what I've been told. So here's my solution, right? That's my solution, which is 2050426. Okay, now here, guys, because I was thinking, how can I explain the identity matrix? So I got this information from the book, from the section here. It says, recall from section 1.1 that a real number 1 is the identity element for multiplication of real numbers. Why is that? Because if you multiply anything times 1, right, it will be anything. For example, 5 times 1 is 5, or 1 times 5 is 5, right? Same thing. So here's what they're doing. They use A as a real number. A can be any number. Okay? So A times 1 is the same thing as 1 times A, which is equal to A. So that's the 1 is called the identity with the real numbers from section 1.1. Now, this is very similar to matrices. But for matrices, the identity matrix, this is not a 1, it's an I. Okay, by the way, it will have the I like, hold on, let me close the door. I'm sorry about that, there was too much noise. Okay, now, again, this is I stands for identity. It's defined that has a property similar to those of number 1. For example, so matrix A, all right, and the identity I, if you multiply them, right, if you multiply matrix A times the identity is going to get the same thing as 1 times matrix A, which is equal to A. Or A times the identity will be A, or the identity times A will give you A. The identity, guys, is always a square matrix. What does that mean? Well, it's going to be a 2 by 2, or a 3 by 3, or a 4 by 4, or a 5 by 5. It cannot be 4 by 3 or 4 by 7. It has to be something like a square, like 3 by 3, 2 by 2, and so forth, right? These are the examples here. Okay, now, example A, matrix A. So say matrix A is this is A, B, A, C, and D. This can be any numbers, right? They can be any numbers. So the identity matrix I will be, right? This is the identity, right? Because we got it from here because it's a 2 by 2. So 2 by 2 will be 1, 0, 0, 1. If you notice, all the ones are diagonal. You see? All the ones are diagonal. So for a 4 by 4, it will be all the ones going like a diagonal from left to right. They're going to be all ones. That's the identity matrix. So then, find A matrix A times the identity. Right, so which is going to be a 2 by 2 because this is 2 by 2 and that's 2 by 2. So the answer will be a 2 by 2 matrix. So here again, we're going to multiply again. So again, the same procedures. A times 1 plus B times 0. Right? The answer is A. A goes there. Right there. It's going a little bit slower here. And then step 2. Right? We have step 2 is going to give us, again, right, we're going to multiply it now A and B times 0, 1 over here on this side. Okay? So A times 0 plus B times 1 gives us B. So the B goes right there. Step 3. Since we're done, right, so there's no more columns to multiply by, then we go to the second row, which is CD. And we repeat the process, C times 1 and D times 0. So the answer will just be C. And step 4, right? Now we're going to multiply to the second column, which will give me C times 0, and D times 1, which will give me D. You see, guys? So when you multiply the matrix times the identity, it's going to give you back the same matrix. You see, this was matrix A. Okay. Okay, now comes the inverse. Hey guys, when you do matrix, you cannot divide. That's one of the properties that matrices don't possess. But you can multiply by the inverse. Because the inverse actually is like the reciprocal. Okay? For example, recall that for non-zero real numbers A, the equation A times X equals 1 has a solution. Namely, if A is 1 over A, right? Because A times 1 over A will give you 1. You see, there's 1 over A. So this is the notation for inverse. With the exponent to the -1, that means it's the inverse. Similarly, for a square matrix, we consider the matrix equations AX equals to A matrix A times matrix X equals to the identity. Okay? So in other words, A times its inverse is the identity. So the A to the -1 is called the inverse matrix. And again here, guys, if you have matrix A times B, here, this example number 10, they're saying, given matrix A and B, determine whether B is the inverse of A. So what do? We're going to multiply them. And if the result is 1, 0, 0, 1, that means it is the identity. And again here, guys, because I don't want to misspend my time, I don't want to go over the hour, and I knew my PowerPoint was going to get actually towards the end. I just gave you the answer, guys. So it is. If you actually multiply them, you will get the identity, which is denoted by the capital I. Okay. So B is the inverse of A because A times B is the identity matrix, which is denoted by I. Okay, now. So here's how you do the inverse of a matrix. The inverse of a matrix A. Okay, this means, okay, this is a matrix here, matrix A, and then slash, and then the identity matrix. That's how you get the inverse. So for example, this means that I'm going to get matrix A, and here's the inverse. So here, guys, you're going to do the Gauss-Jordan elimination method. That's what it wants. That's why it was crucial from the last PowerPoint that I did on the Gauss-Jordan elimination method, how to use it, because you're going to use it here also for the inverses. Okay? For a 2x2 matrix, there's another way to get the answer. But for a 3x3 and above, you have to do it this way. And this is tedious work. So again, you see you have to use the Gauss-Jordan elimination method from 6.2. Anyway, so the object is that you're gonna make that a 0, right? Step 1, and then step 2, you're gonna make that a 0. So you're trying for the identity to come over here. And then whatever is left over here on this side will be your identity matrix. You see, for example, this is my identity. And again, I actually do the work because this is more than an hour. This I'm doing like 2 or 3 sections and it's in an hour, and it's impossible. If you want me to explain this, come see me during my Sunday numbers hours, and I can show you how to do all this. Okay. Okay, now you see for a 3x3 matrix, this is time consuming, and this is tedious work. Okay. Okay, now. So here, guys, again, we're going to use the Gauss-Jordan elimination method from 6.2, and you want for the identity to come on this side, and whatever is on this side will be the identity. The inverse, my bad. You see, guys, so if I do all the work, this is my inverse. So the inverse of matrix A is what's on the right side. That's your inverse. Okay. Okay, now, hey guys, remember for a 2x2 matrix, there's a formula that I didn't see it in the book. This book didn't have it there because I was looking for it, and this is a very famous formula how to find the inverse for a 2x2 matrix without using the Gauss-Jordan method. This is very simple and unique. Okay. For example, say this is the matrix A, right? And these are the elements A, B, C, and D, and these are all real numbers. To get the inverse, you're gonna use 1 over the determinant. The determinant is A times D minus B times C. And then these two, you switch them. You see the D goes there at the corner, on the left corner, the left upper corner, and the A goes to the bottom corner. And these two, you switch signs. Okay, that's how you get the inverse. And this would be my inverse. Whatever you get here, you multiply times every element. Okay? Find the inverse of matrix A, and I think this is one that we did earlier. Okay? I mean the one that I told you that I wasn't going to do the work because you use the Gauss-Jordan method. But this one is much easier to do it this way. You see, for the inverse, it's going to be 1 over 1 times 6 minus 2 times 4. And then what goes here, guys, these two, you switch them. The 6 goes up here and the 1 goes down here. And these become the opposite sign. You see, that's what it means, become the opposite sign. So that's positive becomes negative. If it's positive, becomes negative. Say that 2 was negative, then here it'll be positive. That's what this means here, that you switch the signs. Now, what's 1 times 6 is 6. 2 times 4 is 8. What's 6 minus 8? It's going to give you negative 1 over 2, negative 1/2. So I'm going to multiply negative 1/2 times every element on the matrix here. So negative 1/2 times 6 will give us negative 3. Negative 1/2 times negative 2 will give us 1. Negative 1/2 times negative 4 will give us 2. And negative 1/2 times 1 will give me negative 1/2. So this is my inverse. And that's what we got on the previous slide. Okay, now, this is not for you guys, okay? This is for the students that actually cannot join the workshop, and if they want to get credit for attending, they have to answer these, right? When you're saying what's if we can multiply them, that's all I'm just going to answer. State whether the matrix can be multiplied. That's all something very simple, just to make sure they watch the video, and then they go there and fill out the form. But I believe, Patricia, you have to upload also the one that's not recorded, because this one I don't think he'll let you. I don't know if it
Yes, sir. It's in the chat.
Okay, perfect then. Hey guys, so that's it. But you know what, guys? Let me share my let me see how I can do this. Remember, I promised show you like another way. Let me see how. Again, my computer is kind of acting up here. Let me see if I can get there. I cannot go to my screen anymore. Let me see here. Oh, here we go. Okay, now let me stop sharing. So let me stop sharing. Okay, now, just real quick, guys. Okay, now, can you guys see my board here?
No, sir.
Can you guys see it?
No, sir. Are you sharing your camera, Mr. Azasi?
Okay, let me see again. Can you guys see it now?
Yes, sir.
Okay, check this out, guys. Okay, this is my method of multiplying. Okay, I'm gonna multiply. I think we were multiplying, right? B times A. So this is a method that I came up with. Okay, I'm gonna put my B, which is 1, 0, 4, negative 2, right? And this, guys, cannot be done in pen because you're gonna be erasing. This, you cannot use pen here, guys. Okay, you cannot. I'm gonna put matrix B, and then matrix A, I'm gonna put it here. I'm gonna put 2, 0, 5, and 4, negative 2, and negative 3. And the answer is going to be, right, this is a 2 by 2. This is a 2 by 3, right? So, yes, it can be done. And the answer will be a 3 by 3, right? So the answer will be the same thing as this one, a 2 by 3. Okay, now, here it is, okay? So I tell my students that we're going to be erasing. So this is what you do. When you do it with pencil, you have to write real lightly. Because what we do, I'm going to get the first row, and put it up here. And then I'm going to get the first column and put it here in the middle. 1 times 2 is 2. 0 times 4 is 0. What's my answer? My answer is 2. So then I erase, right? I erase the first column, and I go to my second column. I put it here, right? Because this is is like my placeholder that I tell my students. Again, first times first is 0. Second times second will be 0. So what's my answer? My answer is 0. So then you see I'm done with this column. So now comes the third column. So erase it. I'm going to put 5 and -3. 1 times 5 is 5. 0 times -3 is 0. So the answer is 5. Hey guys, when you're doing it, the long way, the way the book shows you, at times you don't want nobody to bug you because you're into it, because you're concentrating. Here you can even go and come back, and you know exactly where you're at. Okay, so I know that this is my last column, right? So I know this is my first row. Now, right, so there's no more columns, so I know I'm done with this row times every column, so now I put the row number 2. And now I continue the same process. So 2 and 4 goes here. So 4 times 2 is 8. -2 times 4 is -8. So the answer is 0, right? So I'm done here. Then I put the second column, 0, -2. 4 times 0 is 0. -2 times -2 is 4. So the answer is 4. And now I go to my third column, and that'll be my final one. So 4 times 5 is 20. And -2 times -3 is +6. So the answer is 26. And this is my second row. That's how you do it, guys. And after I show my students, they don't like to do it the way the book does it anymore. And on the exams, when I give them to put my matrices, this is a work that I want to see. And I feel so proud of my students because I actually see that work. And it tells me that the way I do it, the modified version, it actually works. Hey guys, do you guys have any questions on that? You can put it in the chat. Or Christina.
No, sir. Thank you very much.
Oh, you're welcome. You're welcome. Okay, now guys, like I said, if you want me to show you the Gauss Jordan method, come see me doing Sunday numbers, because I didn't have time to actually do the inverse the way the book does it with the Gauss Jordan method. It's long and tedious, but like I said, I always try to find an easier way for the students to actually find the solution, and I always have like some kind of plan for the students. Okay, so join me on Sunday numbers, and I'll be more than happy to assist you. Okay. So thank you.
Thank you, sir.
Alrighty, thank you, Mr. Isasi, for the wonderful information and those shortcuts that you taught us about matrix operations. I would like to invite everyone to the next week's events for the Tejano virtual events. Let me share the screen real quick. So we currently covered the basic matrix operations. So next week, there will be a review for exam 3 questions and answers section. So if you have any questions or you want to give us a visit, come join the Happy Math Hour event and we will answer any questions that you have. We do have tutors on standby. So if you have questions regarding the material that was covered today, you are welcome to stay by and they will go ahead and answer your questions. Again, thank you so much to Mr. Isasi for presenting today. And then thank you to the audience for coming and being a wonderful audience. And we hope to see you again next week.
Thank you.